Alright, so today I'm going to show you another bit of mathematical trickery that we use to help us solve integrals that we wouldn't otherwise be able to do. And this is called trig substitution. So what we're going to do is take an integral like this one in example 1 that we don't have a good way of doing. We can't do substitution. It's not something we recognize. It kind of looks like it might be arcsine, but then we have this 4 in here that is just messing things up. So what I'm going to do is just kind of show you how this works, and then we'll talk more about it in later examples. But the key idea here is to use the Pythagorean identities. Okay, so we know we have sine squared, so let's see, I'll write that up here. Sine squared of theta plus cosine of theta equals 1. Okay. Now I can rearrange that, and I can say that cosine squared of theta is equal to 1 minus sine squared of theta. Okay? And now what we can do is we can make a substitution. I'm going to say, let's let x equal, and in this case I'm going to make it 2 sine of theta. Okay? So I'm going to use that. I'm going to, instead of, like when we did substitution before, we took an expression and assigned a variable to it. Okay, and in this case, we're taking the variable and assigning an expression to it, right? So we're letting x be sine of 2 theta. But what that lets us do is if I make that substitution. Okay, so that and I should back up a little bit, because when I make that substitution, well, let me just show you. We get, 1 over the square root of 4 minus, and then when I square x, right, it becomes 4 sine squared of theta, 4 sine squared of theta, okay? And then, but we still have this dx. We have to deal with this dx. So, because I want to now integrate it with respect to theta and not x. So, I have to figure out what dx is. So let's say, so I'm just going to differentiate both sides. I let x equal 2 sine theta, so dx will be equal to 2 cosine of theta d theta. Okay? So, I got to make that substitution as well. So, it's times 2 cosine of theta d theta. Alright, now initially that may not look like a better deal, but you can see now down in the bottom we have a common factor of 4, and it's underneath the square root. So I can bring that out of the square root. Alright, so I'm going to rewrite this. So this is equals 1 over, I'm going to bring out the 4, right? Factor out the 4 and bring it out of the square root. And then I have 1 minus sine squared of theta. And then, of course, I still have this 2 cosine theta d theta. Okay? Alright, so now we can simplify that. We can cross out the 2's because those will cancel each other out. And this 1 minus sine squared theta is cosine squared theta, which is convenient because it's in the square root, and we would like to be able to have we'd like to have a perfect square under the square root so we can get rid of the square root. Alright, so let's simplify that a little bit more. So the integral of 1 over, and then this 1 minus sine squared becomes cosine squared, and then it's under the square root, so we're going to make it cosine of theta. Alright, and then times cosine of theta d theta. Okay, so cosines cancel, and we just end up with the integral of 1 d theta. All right, and that's easy. So that's just theta plus c. Oops, plus c. All right, but we want to get now. We don't want to get rid of the theta now. So we've got to go backwards. So we know that x is equal to 2 sine theta. So that tells me that sine of theta is equal to x over 2. And then And then we can solve for theta. Theta is equal to the arc sine of x over 2. Okay. So now we have theta. So, and of course I'm assuming that you know that theta is between, it's the same, say it has the same range as the arc sine. Okay, so theta is between minus pi over 2 and pi over 2. Okay, so, but anyway, we get arc sine of x over 2 plus c. All right, and that's the final answer. Oops. So you can see now how we can introduce trig functions and use the trig identities to help us solve integrals that we wouldn't otherwise be able to do.